Okay. The lab today is on double replacement reactions. It's a pretty good lab. There'd be a lot of color changes and very similar to the one last week where we had single replacement, where you mark down the observation, then you try to figure out the equation. Today you're going to be doing double replacement. So you're going to be, and then you have a dry lab on practicing doing those long equations. Where you had to do the molecular equation, the total ionic equation, the net ionic equation. And it's a pretty fun lab. It goes really, really well. Most students like it. There's a lot of first aid though required on it. Very similar to what we did for the single replacement. And remember, on the first aid, if the first aid is the same on multiple chemicals, don't repeat it. Well, you can if you want. Just put commas indicating that it's a common first aid for those series of chemicals. Additionally, if we've already done it once in one lab, you don't have to repeat it again. You can just say, see lab 5 or 10 or whatever. Okay. So I don't like busy work and you probably don't either. So I'm trying to minimize busy work, yet get enough information so you're safe. That's the goal. Okay, so today we are going to go into full-blown stoichiometry. And you've heard this word thrown around a little bit. Well, today it's going to be formalized. So are there any questions about anything up to now? Okay. Yeah. Okay. Well, why don't you see if today's lecture makes sense? Because today we're going to go into equations, chemical equations, and see how that relates. So whenever anyone ever talks about stoichiometry, they're talking about moles, grams, liters, gases, and it's the quantitative relationship of those within the chemical reaction. Now, normally stoichiometry requires a chemical reaction. Excuse me. If there's no chemical reaction, you're not worrying about what are you starting with chemically versus what you're ending with chemically. But if there's a chemical reaction going on, you have to take the reaction into account. Now, so step number 1 is going to be balance the chemical equation. Now, I'm going to review, what does a chemical equation give you? It gives you 2 things. Gives you molar relationships and molecular relationships. Not mass relationships. So if you're starting off with grams and they want to know grams of whatever produced, the balanced equation doesn't work with grams. It only works with moles or molecules. So you got to convert. Okay, so here's a typical, oh, let me do one other thing here. The 4 steps, stoichiometric relationships. First thing, if there's a chemical reaction, write it down and balance it. Now, in this class, I'm going to give you the chemical equation. And 1A, and I don't know about 2A, but 1A, you're going to be given the reactants, and then you're going to be required to come up with the products on your own, but not in this class. Bottom line is we have to have a reaction, reactants and products. Next thing is within the word problem, what's being given? And this we've gone over time and time again from day one. Next, what are you trying to calculate? Now, when you're doing this, it's specific for a chemical. If there's no chemical reaction, then the chemical is the same. But if there's a chemical reaction, the chemicals are not the same. So you have to make sure you write down what chemical you're given and what quantity. When you're trying to calculate what chemical it is and what are you trying to calculate. And then lastly, do the setup, just like we've been doing. You start with a given, convert it to moles, then go to whatever. So again, notice moles, 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 and more moles. The typical conversion factors for this concept. We've got molar mass from the periodic table. That's where we add up the decimal numbers of each of the chemicals. Avogadro's number, 6.02 times 10 to the 23rd. That's for any chemical. Molar mass is very, very, very specific. That's why you have to have the formula before you can find the molar mass of a chemical. And then as far as gases go, at standard temperature and pressure, we've got 22.4 liters per mole. And that's any gas. So we have two any's and one that's extremely specific to the chemical you're working with. All right, now you need to know these. I'm going to give you a periodic table. So obviously you don't have to memorize the periodic table, but you need to memorize though Avogadro's number, 6.02 times 10 to the 23rd. And you also need to memorize the gas one, 22.4 liters per mole of any gas. And make sure you know those two. A question came up earlier about a study guide for test 2. The test is Saturday the 18th. And there's a lot in unit 2. So I'm going to be doing a fair amount of review for that test coming up. Okay, so let's look at a typical stoichiometry problem. Okay, we've got 15 grams of methane, CH4. It burns in oxygen to produce water and carbon dioxide. How much water is produced? Okay, so the given is 15 grams of methane. And we're trying to calculate grams of water. So given goes on the left, just like before. We're trying to calculate goes on the right. So step number 1 is balance the chemical equation if there's a reaction. And there is a reaction. Okay, so when we balance this, it's going to be 1, 2, 1, 2 in terms of the coefficients. And let's make sure that's right. So we have 1 carbon on each side. We've got 4 hydrogens on each side and 4 oxygens on each side. So it's definitely balanced. Okay, is everyone okay with balancing equations? Now, I want to tell you right up front, it's the first step. If you don't balance the equation correctly, guess what is wrong? What the whole problem then is wrong, the rest of it. So it's crucial you balance the equation correctly. Okay, so the essence, when you have a chemical equation, we can use the ratio of the coefficients to determine how those react. So we're looking at methane and water. So the relationship between methane and water is a 1:2 ratio. Just like in lab 10 on hydrates, we were looking at the ratio of water molecules or moles of water versus moles of copper sulfate. There's a ratio there, and that determines the N value. Okay, so we don't care about anything else. All we care about is the coefficient for the given and the coefficient for the calculated. Okay, so we're going to start with moles of methane. Okay, moles of methane, we need to find the molar mass for CH4. Okay, that's going to be one carbon, which is 12.01, and four hydrogens at 101 apiece. So that's one carbon, four hydrogens. Does everyone see where I got the 4.04? 4 times 101 is 404, okay? And you can do it one hydrogen, 101, one hydrogen, one, or you can just multiply in your head what that is. And it's easy with hydrogens because it's 101. Some of the other ones aren't that easy. Okay, so we're looking at 1605 grams per mole for CH4. Water, we have one oxygen at 16, and we have two hydrogens at 202. Okay, so definitely need the molar masses for the given, molar mass for the calculated. All right, so our first step is to convert the 15 grams of methane to moles of methane. Okay, so grams have got to cancel. And that is 1605. Now we have moles of methane. And the ratio between the moles of methane to the moles of water is 1:2. So that's the next step, is to do the conversion from one mole to the other mole. And the methane needs to go on the bottom so it cancels. Now, if you look online for a tutorial on stoichiometry, sometimes they'll say 2 moles water to 1 mole methane. Now, it's optional for you to include that. If it makes more sense to put it down then. Now we have moles of water. We don't want moles of water, we want grams of water. So now we're going to go from moles of water to grams of water. To do that, we need the molar mass of water. That's why we calculated over here. So moles need to be on the bottom to cancel. So what are we left with now? What is not canceled? Grams and water. What are we trying to calculate? Grams of water. So we know the setup is right. So you're going to multiply everything on the top, divide by everything on the bottom. So this is basically 3 steps whenever you're doing stoichiometry. All the time. No exceptions. First step is to convert to moles. Next step is you have the molar ratio from the periodic table. The last step is to go from moles to what you're trying to calculate. Okay, so this is going given to moles. So 3 parts. First part's convert to moles. Second part is you're looking at the ratio of the coefficients from the balanced equation. You want to put what you're starting with on the bottom so it cancels. On the top is what you want to end up with. Then lastly, you're going from moles to whatever you're trying to calculate, whether it's grams, liters, number of particles, number of atoms. Okay, so always 3 steps. Now, if you look at some practice problems, you go to Canvas, Files, Stoichiometry. You've got a whole bunch of worksheets here. And of course, here's your extra credits. Has anyone tried it yet? Okay, I want you to drink lots of coffee before you start and make sure you're not nervous. You need to be really relaxed to do this problem because it's a pain, just FYI. And also don't be afraid of large coefficients. I'm saying like over 100. Don't be afraid that they're getting big because they are going to be big. There's a lot of people that stop working this because they're going like, we've never done a problem where the coefficients are like 150. Usually they're like 4 or 5. So I'm just giving you a heads up. The reason why it's extra credit, because it's not easy. Okay, and then also there are additional worksheets, and I don't want you to do any yet. The ones that say limiting reagent. Now tomorrow is going to be a review day for this. This is one of those topics in 1A and 2A that people frequently mess up on. So I want to make sure it's really solid for you. I mean, solid. So tomorrow is going to be a workshop kind of deal, okay? In fact, what I should do, I have to remember to do this. I'm lately I've been forgetful, and I've got a lot on my plate. And let me just send myself a note to remind myself to print off a tomorrow worksheet for you guys, and then we'll just work it as a group. So if you don't want to come tomorrow for the lecture, there'll be no new material. It'll just strictly be review. Shouldn't be saying that, but it's going to be review. um, all right. And then next week on Friday, we're going to get into a special case. It's called limiting reagents. So don't do any of the worksheets yet, practice worksheets. It's a limiting reagent. That's where you have two givens instead of just one given. So it's quite a bit more work. So, but you got to understand what we're talking about today and tomorrow really well before that makes sense at all. Okay. All right. So let's. Okay. So did this setup make sense? Any questions about this setup? All right. Now, I want in your mind to take a picture of this. 3 parts to every one of these. Beginning part, go to moles. Middle part, mole ratio from the balanced equation. Third part, convert from moles of what you're trying to calculate over to, grams or liters or whatever. Okay, 3 parts, every single one. Boom, boom, boom. Okay, using the same reaction. 29 grams of carbon dioxide is produced. How much oxygen was consumed? Okay, so the given, we always go to the number 29 grams of carbon dioxide. And we're trying to calculate when it says how much, that is, think in terms of mass, so that'd be grams. Now, same setup, 3 parts, same setup. First step is take that 29 grams to moles. So now we have to calculate the molar mass for carbon dioxide. Okay, so carbon dioxide is 1 carbon. Oh, got it right over here. So we have 1 carbon, 2 oxygens. Excuse me. So that's 4401 grams per 1 mole. So grams cancel. Now we have moles of carbon dioxide. So the ratio of oxygen consumed to carbon dioxide produced is 2 to 1. So it takes twice as many moles of oxygen to produce each mole of carbon dioxide. 2 to 1 ratio. That's the next step. So carbon dioxide needs to be in the bottom, so it cancels. oxygen on the top. So that's 2 to 1. And again, from the balanced equation, and this is why we balance the equation, to get this ratio. Now we have moles of oxygen. Now we need to go from moles of oxygen to grams of oxygen. And oxygen is O2. That means it's 16 twice. So it's 32 grams. Moles are going to be in the bottom, so they cancel. So what are we left with? Grams of oxygen. That's what we're trying to calculate. Grams of oxygen. So you multiply everything on the top, divide by everything on the bottom. Three sig figs, 4 sig figs, infinite sig figs. Why is it infinite sig figs on the ratio from the balanced equation? Why isn't it 1 sig fig? Hmm? Yes, that's right. It's indefinite because it's perfect. Okay, it's not measured. We make it perfect. So that's why it becomes infinitely precise. So that ratio sig fig wise doesn't come into play. And then this is 4 sig figs. So our answer is going to be 3 sig figs. And again, a lot of my stuff is 3 sig figs because I'm used to using a slide rule. Slide rule is only accurate to 3 significant figures. And until 1976 or so, I didn't have a calculator. I had a slide rule. So ever since high school, the 76 slide rule, and I went through quantum mechanics, physical chemistry, thermodynamic, advanced thermodynamics with a slide rule, 3 sig figs. You see, if you've watched the movie Apollo 13, one scene is the whole room with about 60 or 70 engineers. And they all had slide rules. And that got us to the moon. The computer that they used was a IBM PC-1 with no hard drive. It was 2 floppy disks. That was it. Got us to the moon. Okay. So anyway, hence 3 sig figs. So, okay. So multiply everything on the top, divide by it, everything on the bottom. Again, 3 parts. 3 parts. Convert to moles, mole ratio, balanced equation, and convert to whatever you're trying to calculate via the moles. How are we doing? Is this making sense? You're all nodding. I see one person nodding, yes. Okay, let's just keep going on this now. Now your book does a very good job on explaining this as well. So also there's some nice example problems in your book. So this is a really good resource. By the way, as I said before, I'm thinking about going to a free public domain textbook for next semester. When I heard the price of this book, took a double take. You know. Okay. I keep using the same equation because it's easy to balance, but it doesn't matter what the equation, got to be balanced. Okay. And whenever we're dealing with oxygen gas, any of the gases, for our class, Chem A, it's at standard temperature and pressure. Hence, the 22.4 liters per mole works. If it's not at standard temperature and pressure, you have to invoke something called the ideal gas law first, which is yet another equation. Complicates things. Okay, so 23 liters of oxygen is consumed. How much methane is burned? So given this 23 0.4 liters, we're trying to calculate how much. Again, how much we're talking about is grams. So we're talking about grams of methane. Okay, so we need to go to liters to moles. Now we have moles of oxygen. Now comes the ratio from the balanced equation. So we're looking at oxygen and methane. So the ratio is 2 to 1. 1 mole of methane requires 2 moles of oxygen to be consumed. So O2's got to be in the bottom, so it cancels. And the molar mass for CH4 is 1605. Oxygen cancels. So as you're doing this canceling bit, take it before you take out your calculator. Make sure everything is canceling. So what's ever left over is what you're trying to calculate. It's really important to do that because we have some inversions here that are also valid. If you don't get the inversion right, your answer won't come out right. Notice a pattern. The setups look the same. Yeah. Because I didn't give you grams. I gave you liters. So that's why you had to use the molar gas volume. That makes sense? Okay. What if I change this problem? to how many liters of methane. What would change on the setup? What would be different? Well, yeah, we're going to be looking at the 22.4 number again, because we're going from liters to moles or moles to liters. So instead of the molar mass, because that gets us to grams, we need to use the 22.4 liters per mole to get us to liters. So this step here is going to be 22.4 liters. And this will now give us liters of methane. Again, it's molar relationships. It's moles, 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 moles. Now our next unit, unit 3, we're going to be talking about liters in solution. And guess what? Moles per liter, liters per mole. Again, this mole bit keeps coming back, and coming back, and coming back. So it'd be 11.7 liters. Five grams of water is made. How many liters of oxygen were consumed? So given is 5. Now notice it doesn't matter where the given is and where the calculated is. Like in the previous problem, everything was on the left side of the equation. This one, the given's on the right. We're trying to produce something on the left. So don't get the left and the right part of the equation requirement. There is no requirement. It's just find the given, find what you're trying to calculate. Okay, so here we're looking at water and oxygen. Okay, water's from our previous calculation is 1802. The ratio is 2 to 2 for oxygen and water, or 1 to 1. And then we need to go to liters of oxygen now. So now we're going to be using the (22.4). And of course, it's at standard temperature and pressure. So we have 3 sig figs, 4 sig figs, infinite sig figs. 3 sig figs. So our answer is going to be good old 3 sig figs. So we're looking at three parts again, 3 parts. Now I'm doing these examples purposely to show you how consistent every problem is. Every problem's got the same setup. Get it to moles, mole ratio, go from moles to what you're trying to calculate every single time. So a lot of you look for patterns in your problem solving methodology. Well, this is the pattern. Let's do one that's slightly different. Let's do this one here. Okay, 23.7 liters of methane are burned. How many molecules of oxygen gas were consumed? Now we're talking about how many. So what conversion factor are we going to be using for that? Good old Avogadro's number. How many? That's counting. All right, so we're starting with the equation that we've been using forever. And let's run up and grab that. And remember, all chemical reactions are two-way. Two-way. And this is going to be really important in 1A because you're going to be talking about something called equilibrium. And that's a two-way street. So I want you to start from right from now, thinking that a chemical reaction just is not one way. Not one way. Can you remember we formed the activated complex back when we were talking about the graph and potential energy and all this stuff? Remember, at the top of the activated complex, things can fall back to the reactant side, things can fall back on the product side. That's why it's two-way. Okay, so 23 point liters we start with, and that's of methane. And for our class, since I didn't mention, we can use the standard temperature and pressure relationship of gases. Now we have moles of methane. Now we need to go to moles of oxygen. So that's going to be a 1-to-2 ratio again. And now we want to know how many molecules, how many molecules. That's Avogadro's number. So CH4 cancels, moles cancel. We're left with molecules of oxygen. And don't forget to use your EE function. Okay, so that's a good example of a nice variety of problems. Now, I'm going to mention something else. Some books or some tutorials online, when they say oxygen, they really mean oxygen gas, because O by itself does not exist. It always exists coupled with something else. So if they just say oxygen without saying oxygen gas, it's O2. There are 7 diatomic gases. And those are listed. There's nitrogen, oxygen, all the halogens. So there are 4 groups basically. All the halogens. So that's F2, Cl2, Br2, I2, helium, nitrogen, and oxygen. So there's 7. But if you just remember the hydrogen, nitrogen, oxygen, and all the halogens, it's only 3 to remember. Okay, now I always try, and I'm not perfect, as you well know. When I mean oxygen gas, I try to say oxygen gas. And sometimes I just say oxygen. Particularly book problems will just say oxygen. And it bugs me they don't say oxygen gas, but they. All right. Okay. Okay, this is a little different slant. 2.34 times 10 to the 34th molecules of methane are reacted. How many liters of gas, oxygen gas, are consumed? And of course, at STP. So we're starting with okay, so molecules of methane. We're going to end up with liters of oxygen gas. So again, first step, get to moles. Okay, if we're given molecules, you have to use Avogadro's number to get there. Now we'll use the ratio from the balanced equation, which, let me write that down here. So we're looking at 1 to 2. We want the CH4 on the bottom, oxygen on top. We want liters of oxygen, liters. So that's a 22.4 liters. Moles cancel. CH4 cancels, leaves us with liters of oxygen. Now, in this problem, it's crucial you use EE on the bottom. If you don't want to use EE, make sure you put the 602 times 10 to the 23rd in parentheses. Otherwise, your calculator, being dumb as it is not going to interpret your calculation the way you intended it to be. So this is 3 sig figs, 1.74 times 10 to the 12th liters. That's a lot of liters. Okay, so what would be good, this is basically what I wanted to cover today. Basic stoichiometry. Now tomorrow, we're going to do a lot of practice problems. A lot of practice problems. So you could do two things. You could do nothing between now and tomorrow, or tonight you might want to review your notes from today before we start tomorrow. Now next week we're going to start with two givens, and we are going from one of these equations in red here to 4 of them per problem. So your problem is going to end up taking up a whole page of paper on problem. That's why it's absolutely a requirement to understand the simplified version. Absolutely, because you will be blown out of the water next Friday. Okay. All right. So today's lab is really a nice lab. Double replacement reaction, goes fairly fast. It's kind of cool. You got colors going on. On your phone, bring up the solubility table we did last time. We need that in lab. All right. Are there any questions about this process? Hopefully you see this same thing happening each time. Boom, boom, boom. 3 parts every single time.